What we now have is a very important principle about the circumstances in which the amount of capital per person, the per capita capital stock, the capital labour ratio, in other words, when can that possibly change? And it's a story about saving and investment. It's a story about there being some resources left over from saving after we've taken care of our replacement investment, with those resources then being able to be used for net investment, and in doing so grow the capital labour ratio. Keep that in mind as we go through these next few slides, and that's going to be a very important notion for us as we develop the Solow Swan approach model of economic growth. So, as we have seen, we are going to have a very simple hypothesis, a very simple theory of saving, that the economy's saving is a constant proportion of its income, so that on this particular diagram I can draw both the per capita production function and also what's called the per capita savings function. In other words, you can tell me any particular capital labour ratio, and I'll be able to tell you by reading off this diagram what the corresponding per capita income will be. And once I know per capita income, I can tell you what the corresponding per capita saving is. And remember, once I know how much saving is going on in the economy, I have a measure of the resources that are available for investment. One more piece of information that I need to add to the analysis, and then in fact we have a pretty comprehensive picture of the entire economy. The final piece of information I need is a line which tells me how much replacement investment is going to be needed for each and every level of the capital labour ratio. And that's this, the replacement investment schedule, as it's called. You remember the argument about why it has this particular form, that the amount of replacement investment is going to depend both on the size of the capital labour ratio, but also on the rates of population growth and depreciation. And in an exercise, I'll ask you to vary some of those terms and see what happens to this replacement investment line. The way to think about the replacement investment line or replacement investment schedule is it tells us what needs to happen at each and every level of the capital labour ratio, given the rates of population growth and depreciation. What has to happen to exactly offset the effects of population growth and depreciation? What has to happen to stop the capital labour ratio from falling? So it's a bit of a guideline, if you like. It tells us something about the resources that will be needed for each and every capital labour ratio to stop that capital labour ratio from falling. And now I want to identify for you one of the most important, certainly one of the most famous concepts in economics, and it's at the absolute heart of this Solow Swan approach. This is a situation known as the economy's steady state. What is the steady state? As the name suggests, it's a situation where if the economy was to find itself in this position, in this situation, nothing would subsequently change. In this analysis, the steady state is identified with this particular point on the diagram, which I'll call point. I'll call it point A asterisk. It's nothing to do with total factor productivity. It's just a label I'm attaching to that point. What I'm saying here is that should the capital labour ratio happen to be at that particular value, let's call that K on L star, Now, I'm not going to address whether the economy will be at that point. We'll come to that very shortly, but let's just suppose it was. That for some reason, the economy's capital-labour ratio was at that point, K on L star. There would be a corresponding level of per capita income in the economy through the production process given by Y on L star. That would generate a flow of saving that exactly corresponds to what the economy's replacement investment needs would be at K on L star. So to repeat, what's going on here? If the economy happened to find itself at a point consistent with A star, in other words, if its capital labour ratio was this K divided by L star, there will be a flow of savings being generated at that particular point that would be exactly equivalent to the economy's replacement investment needs. No more, no less, but exactly equal. What does that mean? It means there will be no change to the capital labour ratio. We've exactly offset the combined effects of population growth and depreciation, but we haven't any resources left over from saving once we've done that to engage in any net investment. So the capital labour ratio would not change, and the economy, unless something should happen to alter these circumstances, would remain in this position, hence the term the steady state. This is an economy where there is no economic growth. There is no change to per capita income. It really, literally is a steady state. The obvious question to ask then is, well, so what? So there is this steady state. It's just a theoretical possibility. Is there any reason to believe that an economy might find itself in such a position? Well, in theory, the answer to that question is unambiguously yes. And to see why, suppose the economy wasn't at the steady state. And this is a very common technique used by economists to take a situation different from the one we are actually considering and seeing if that makes any difference. So let's consider two circumstances where we're not at the steady state. The first circumstance will be, suppose the economy, for whatever reason, finds itself with a ratio of capital to labour, let's call it K divided by L prime, which is actually higher than the steady state. What would happen then? Well, I want you to look carefully at this diagram and note the following. Should the economy's capital labour ratio be at this particular point, with a very high capital labour ratio, the economy's need for replacement investment is going to be quite high. A lot of resources will need to be devoted to replacement investment to offset the population growth and depreciation. Where are those resources going to come from? Well, we have a problem. We are getting some of those resources from saving, but not all of them. We have this gap. The economy's need for replacement investment exceeds the amount of saving that's being generated. This means we can't fully offset the effects of population growth and depreciation. Not possible. We don't have enough resources to keep the capital labour ratio from falling. And that's what would happen next. The capital labour ratio would start falling. As the capital labour ratio falls, our need for replacement investment also correspondingly falls. And as the capital-labour ratio falls, the per capita income being generated in this economy also falls. And as a consequence, less resources will be needed for saving. So you can see what happens. We are taken to the steady state. Once you're at the steady state, the process will stop. There'll be no further reduction in the capital-labour ratio. We will be literally at the steady state. So what's the key message from this analysis? Should the economy find itself with a capital-labour ratio which is higher than the steady state, insufficient saving will be generated to meet the economy's need for replacement investment, the capital-labour ratio will fall, and the economy will find itself in that steady state. What if we had the opposite circumstance? And this is one I really, really want to emphasise. This is crucial. What if the economy found itself with a capital-labour ratio, let's call this one K on L double prime, which was to the left of the steady state? Well, once again, we have a gap. But it's a different sort of gap to the one from the previous slide. What we now have is a situation where if we have the capital-labour ratio K divided by L double prime, we have a situation where the saving generated by this economy is going to be larger, as you can see, larger than its need for replacement investment. What does that mean? It means there are resources left over for net investment. So net investment can be a positive number, which is what I mean by that little expression there. What does net investment do? Net investment grows the capital-labour ratio. And what does growing the capital-labour ratio do? It grows per capita income. As the capital-labour ratio grows, the economy's need for replacement investment grows, but so does its saving. And this process continues until once again we're in the steady state. Think about what we've shown in this slide. What we've shown in this slide is, in fact, economic growth. And that's one of the main contributions of the Solow Swan model. It actually clarifies for us what we mean by economic growth. Economic growth, this moving around the production function, this increase in per capita income, is actually an economy moving towards its steady state. When we see an economy growing in this framework, we are looking at an economy that has an actual capital-labour ratio below the steady state. And what we call economic growth is actually movement towards the steady state. When you think about what we've shown here, that's quite remarkable. Look at the diagram. There are two axes, three lines, some very simple concepts. In particular, the link between saving and investment that we know from the national income accounting work that we did previously. This simple framework, two axes, three lines, and we now have a very profound insight into the nature of economic growth. When we see economic growth, when we see growth in per capita income, we are looking at an economy travelling towards its steady state. That's actually a pretty important and powerful message, I think, that comes out of this framework. However, it is troubling in one respect, and you've probably thought of this already. This is a series of lectures on economic growth. This is a series of lectures that began with an observation for the United States that's repeated in a wide variety of economies around the world of what looks to be a continuous process of economic growth over very long periods of time. Why is it that in the United States, Western Europe, Canada, Australia, many other countries, why do these countries, why do these economies have such long histories of economic growth? Why aren't they reaching their steady state? So many people look at the Solow Swan model and scratch their heads a bit and say, well, look, that's all very interesting, it's a very nice model, I can see why you like it, but it can't really help us, can it? Because this is a model that predicts an end to growth. This is a model that says, well, you just sit back and wait, and eventually per capita incomes will stop growing. But my view is that's the wrong way to think about the contribution of the Solow Swan model. What the Solow Swan model shows us is that unless something changes in this framework, the inevitable result is a steady state and an end to growth. The fact that we see so many instances in the real world of long-run growth tells us that there must be something else going on, something else that means the attainment of that steady state is not yet happened. Now, there are two obvious candidates for that. One probably not as important as the other, but I'll deal with that one first. And that is, what if there's an increase in that savings ratio, that number theta? What if it went up from 40% to 50%? Would that make a difference? Well, let's conduct an experiment. Let's take an economy initially at a steady state in A star. And let's now increase the savings rate. How this happens is not really important for this demonstration. It may be that people themselves make a conscious decision to try to put aside more resources. There might be a government here who mandates in some way that more resources are withheld. It doesn't really matter. For whatever reason, this is a society that has decided to withhold more resources from current consumption, therefore to make those resources available for the purposes of investment. So we start at A star, and then we increase saving. So the savings rate moves from theta 0 to theta 1, from 40% to 50%. So the saving function shifts up. What implication does this have for the economy? Well, what you can see straight away is a new steady state. A star is no longer the economy's steady state. The economy's steady state, once the savings function has shifted up, becomes B star. What does that mean? It means that that capital labour ratio that was initially associated with that particular steady state is now associated with a flow of saving which is greater than replacement investment. We've seen what happens under these circumstances. We know that under these circumstances, where there is more saving than what is needed for replacement investment, that net investment can now take place. The capital labour ratio can grow. As the capital labour ratio grows, so does per capita income. You get some economic growth, and the economy then travels. It'll travel to that new steady state. So one way in which an economy can grow once it's reached a steady state is to increase the savings rate. However, it's not quite as simple as that. It's not quite as simple as that for two reasons. One is that eventually we get back to the steady state. It's a new steady state. It's a new steady state which has a higher capital labour ratio and consequently a higher level of per capita income than we had originally. So in some sense people are richer, but once you get to the steady state, growth stops. So this increase in saving gives you a temporary period of economic growth, but it doesn't give you economic growth forever. The second important consideration here is there are limits to how many resources can be put aside for the purposes of saving. Current needs have to be met. It would be a very foolish society indeed that saved all of its income, had nothing to meet its current needs, and so this process of increasing the savings ratio as a means of getting at least some temporary growth, there has to be limits to how often that can take place. There are limits to how sensible it is to increase the savings rate.